All right, good morning. We're going to run through the derivation for the recent free response question about the electrical circuit. So here's the problem. We have this circuit. There's a battery with some EMF, and there's 3 light bulbs. I have these represented as resistors here. The value of all the resistors is the same. And we have bulb number 1, bulb number 2, bulb number 3 with a switch connecting these. Now the initial state is the switch is open, so there's current passing through bulbs 1 and 2 in the circuit here, and bulb number 1 is dissipating some amount of power, which we call P1. So this is the given information. What we're supposed to find is the power, which is P1 final. That means with the switch closed, and we want to express that in terms of the power 1 when the switch is open, the initial state. So we're comparing the initial state to the final state. Now what are our goals here? How are we going to get there? First thing we're going to do is we're going to find P1. So that's the initial power radiated from P1 while the switch is still open. Then we're going to come up with an expression for P1 final. So that will be the power dissipated from bulb 1 in the final state, which is with the switch closed. And then we're going to combine those two terms so that we can express the final power in terms of the initial power. So that's our strategy. That's the steps we're going to be going through here. So let's start off with P1, and the equation that we're going to use is V1 squared over R. Remember, power is V squared over R. Now, why are we choosing this one? This is a very good question. All right, well, because we have to express both of these things in terms of something that does not change. Now, the voltage of the battery does not change, so having voltage in the term is useful, and the resistance of the first light bulb also does not change. So the voltage is going to be constant in both situations, and I'm talking about the battery voltage now. The battery voltage is going to be constant in both cases, and the resistance of the resistor itself is going to be constant in both cases. Okay, so we want to be able to feed this. So to be able to find the voltage drop, that's what V1 is. V1 is the voltage drop across this resistor. To be able to find that voltage drop, we have to know the current which is passing through that resistor. So first we're going to find, let's see, I'll just kind of put a barrier here. We're going to find I1, the initial current in the initial state. How are we going to do that? We're going to say that we're going to use Ohm's law. I is equal to V over R. This is, and this current here is the current which is leaving the battery. And that's what we want, because the current leaving the battery is also the current which passes through this first resistor here. So we're going to find the current leaving the battery. The voltage here is the battery voltage, and the resistance is the resistance that the battery experiences. So that means we have to figure out the total resistance of the whole circuit in its initial state. Now in the initial state, it's pretty simple. We can just say that this is equal to V, the battery voltage, divided by 2R, because when you have resistors in series, you just add them up. So 2R. The resistors have the same value, so that's where we are. So if we now, so this is the current which is flowing through the first resistor. So now we want to know the voltage drop across this resistor, because we need that to feed our equation here. So V1 initial is equal to IR, using Ohm's law again. But now we know that the current flowing through that resistor is V over R, so this is equal to V over 2R. That's this term here for the current, times R. The R's are nice enough to cancel out, and we find out that the initial voltage, or the voltage drop in the initial state, is equal to the battery voltage divided by 2. Now, this shouldn't be too surprising because we have 2 resistors at work here, and half the voltage is going to be soaked up by the first one, and the rest of the voltage is going to be soaked up by the second one. Now, a lot of you saw that right away. Good on you, but not everybody does. Now, how are we going to use this? Because our voltage drop is V over 2. So now we can go back and plug in our terms for the actual power drop. P1 is equal to V1 squared. So that is V over 2 squared. This is P1 equals, run myself out of room here, times 1 over R. So this term here is the numerator, and I've broken it out times 1 over R. When you work all this out, you get 1/4 V squared over R. I better do that more neatly. Okay, so let's do this again. We're going to do V squared over 4. That is V over 2, quantity squared, times 1 over R, and that is equal to 1/4 V squared over R. And that is equal to the power through the first bulb in the initial state. Now we're going to do the same thing for the final state. We're going to close this switch so we have current flowing through both of these. That's going to change the total resistance, but we're going to work all that out, and we're going to find what the power dissipated by the first bulb is in the final state with the switch closed. Again, we're going to use V1F squared over R. That's where we're going with this. So this will be the voltage drop across the bulb in the final state with the switch closed, divided by the resistance of the bulb itself, which does not change. So again, we're going to have to find the current flowing from the battery with the switch closed. And in this case, we're going to have I is equal to V over, same thing, we're using Ohm's law here, I equals V over R, but what is this term for the denominator? Well, the resistance is going to be, the total resistance of the circuit is going to be this resistor, which is in series with these 2 which are in parallel. So we'll start off with the first one. The resistance is going to be R of the first resistor plus 1 over R plus 1 over R. Okay, so we're doing kind of a equation within an equation here for resistors in parallel. Now I'm going to reduce all this down here, and we get R plus 1 over 2R, because 1R plus 1 over R plus 1 over R is 2 over R, so we have 1 divided by 2 over R, which itself is equal to R over 2. So we have R plus R over 2, easy for me to say and write at the same time, and this all comes out to be V over 3/2 R. Okay? So the current coming out of the battery is equal to the battery voltage divided by 3/2 R. And we can simplify that further and say that it is equal to 2/3 V over R. Okay? You can pause it there if you need to puzzle that out or work that out on your own, but that's what you should get as an intermediate step. So the current coming out of the battery with the switch closed is 2/3 V over R. Okay, now we need to figure out what the voltage drop is across the first bulb, because we need that figure to figure out the power dissipated by the bulb. So again, we have V V1 final state is equal to IR. Since we just figured out that the current is equal to 2/3 V over R, that is 2/3 V over R times R. So this first term is the current. The second term is the R that we need from V equals IR. The R's cancel for us again. We find out that V1 final, the final voltage drop, is equal to 2/3 of the initial battery voltage. So the V1 final, that's the voltage drop across this resistor. The V in the other term is the battery voltage. I'm using V instead of the EMF symbol because I find them easier to draw. Anyway, now we need to know the power dissipated in the final state. So we're using this equation again. P1 final is equal to V1 final squared over R, which equals 2/3 V quantity squared times 1 over R. That comes out to 4V squared over 9. That's what that is. So we get 4V squared over 9R. 4/9 V squared over R. That equals P1 final. So we know P1 initial is 1/4 V squared over R, and P1 final is 4/9 V squared over R. Now we're going to combine them because the V squared over R is a common term in both of them. So we'll start off here and we'll say that P1, which is equal to 1/4 V squared over R, will come down to let's see, 4P1 is equal to V squared over R. Now at the same time, P1 final is equal to 4/9 V squared over R. So pulling out the V squared over R, that means that P1 final, we have 9/4 P1 final is equal to V squared over R. We put the 4/9 over on the other side. V squared over R is the common term, that's why it's in the middle. So we get 4P1 initial is equal to 9/4 P1 final. Now we need to express all of this in terms of the initial P1. So we're going to multiply this across, and this goes to 16/9 P1 initial is equal to P final. So what's our goal? Our goal was to express the final power with the switch closed in terms of the initial power. The initial power was P1. We multiply that by 16/9, and that gives us the final power, and that is the answer. Okay, I hope this was helpful. I mentioned at the start, these are considered the most difficult questions on the free response questions, and the reason is because they take so much time. Now, I went through it very slowly, but if you look at the timer, you'll probably see that I spent at least as much time as you had for the entire question, and you can't be spending that much time on the AP exam. But I was trying to go through it step by step so you could follow me. You need to practice these sorts of things so you can be quicker with them. AP will give you partial credit. So if you have this answer, you get a point. If you have this answer, you get a point. And if you're able to put them together into final form, you also get a point. So driving your way through part of it will help you out. Let's summarize here the strategy. We want to find an initial state and find a final state, and then we want to find some common terms between those two expressions to let us combine them into expressing one in terms of the other.